Hello, monkeys, bitches, and whores. Today we are gonna be going through the long-awaited HAX assembly language, and so bear with me. This is some of you might think this is a boring lecture, but this is not Rapal's lectures. This will be fun. It's pretty simple. I'll go straight through it. It won't be a long video. I'm just explaining the basics, and next lecture we'll go a bit more advanced and go through the practice and other things. Now, when you were talking about a HAX or an RTL, what they mean, so your RTL, all right, is the register transfer language. Okay, register transfer language. Now, what this means is the transfer of data of registers. So when I say A, arrow, B, let's say I'm putting B into A when I do, PC into PC plus 2. I'm doing PC plus 2 into PC. And so that's the language, and I'll teach you more about the language in a bit. And then we have something called a HAX. Now, what a HAX is a hypothetical academic example, or a hypothetical. I think I can write it, and I can't say it. Hypothetical academic computer system. So it doesn't really exist. We're just using it so you understand how a computer actually works. Right now, computers, obviously there's so many different architectures. There's the Ryzen CPUs, there's Intel CPUs, there's ARM CPUs, there's Apple Silicon CPU, and they all have different architectures. But we're gonna be using HAX because it's hypothetical, and it gives you a good idea of what happens. Now, this hypothetical, this fake computer or CPU we're talking about, has a total of 256 bytes of memory, right? It has a 4-bit opcode, and we'll talk what an opcode is. It has a 4-bit padding and an 8-bit operand. I don't know. These parts you don't really know. The opcode maybe you'll need to understand, which we'll go through. So it's not too bad. It has an 8-bit path. This is for transferring data. You don't really need to know much about that either. 7 8-bit general purpose registers. So these are registers, general purpose, that store data that the CPU is using. All right, and these are general purpose. They're not made for a specific thing. You can use them for anything else, really. And then we have the special purpose registers, and this is what we're actually going to be working with. This is the important stuff. This is the juice. All right. For this, I'm going to do a little drawing. All right. So we have a big ass CPU. All right, and then we have a RAM. There you go. And so this is our RAM. And this RAM, obviously, holds some memories. And this is our CPU. Now, inside the CPU, you have a couple things. A couple little boxes. You have this box that is called your PC. Now, what does... Let me do this box better. This PC is your program counter. Now, what does this keep track? This is actually a pointer. And this pointer points to where you are at the instructions. So usually, if you're just starting a program, you'll start at the top at position 0, right? Then, after you finish this instruction, whatever is written here, you finish it, the pointer will move from here to the second one. And so it keeps track of which instructions you're doing in order. You're going from 0 to 1 to 2 to 3. Right? As soon as you finish the instructions, it increment and it goes, this is the next step to do. Like this is the next job. It keeps track of the jobs. All right? Now, then you also have an IR. And by the way, don't think this is actually how it's built. I'm just trying to explain it. There's something called an IR, and this is the instruction register. Now, what does this do? You know how we said PC holds the instruction? Now, PC only holds a pointer to the instruction. It doesn't tell you what the instruction actually is. And then so when it grabs it, let's say you finish this job and it goes to the next one. What happens is here, we're going to take whatever the address PC found, we're going to take the actual instructions and put it here. So whatever the writing here becomes here. Okay? So PC holds address, or yeah, address of next instruction. All right? So address of the next instruction. And then IR stores the instruction opcode, which is what the instruction actually is. All right? So IR stores what the job actually is. Right? And then you have a MAR, which is a memory address register. This address holds the memory of what you're trying to do stuff to. Okay? And then so here, let's say we have a MAR. Okay? And so this MAR, let's say I want to move. So here, let's put some actual data here that we're going to try to manipulate. Let's say this is a, actually, so we have our, remember we have up here, general purpose A, B, and C. So we're only going to use register A, and we're going to put it here. This is going to be our register A. Now, what does register A do? It holds information that CPU needs. And what I mean by that is, let's say there's here some code 01100, and the CPU needs to do some addition on this. This will be dragged and put in here, okay? Because this is what you're going to operate on. It's a small memory inside the CPU that gives it quick access, okay? And so let's see, let's move A. Actually, let's move B into register A. All right. So let's say this is B. And so first, my obviously PC holds a pointer to B. So then what we're gonna do is, well, here the instruction is right, move. So PC will go here and it will say the instruction is move. Now the IR is gonna be like, well, what are we moving? The CPU will read the rest of the instructions and I'll be like, oh, we're moving B. So we're going to take the address, of B, and we're going to put it into the MAR. So address of B. All right. And so PC holds what's the next instruction, and then IR holds what the actual instruction is, and then your MAR holds the address of the thing you're trying to manipulate using this using the move, you know, like what am I trying to move? So I'm gonna hold the address of the thing I want to move. All right. And then the CPU, which is, I'll have like some logic, ALU or whatever you want to call it. This is gonna be the brain, let's say, or the manager. We don't really explain much about the manager because it just does things. So the manager goes like, I'm gonna read the instructions. The manager is basically connected to everything. All right, because it controls everything. It tells everything what to do. Right? And so what it does is, first, it tells PC, go to the next instruction. What's the next step? PC will do it. Then it will tell PC, hey, move it to IR. Then it moves the instruction to IR. Then the manager goes to IR. It reads, hey, what do I got to do? Oh, I got to move? Okay, thanks. Then it goes to MAR. It goes like, what am I trying to move? What's the address of what I'm trying to move? So the MAR will go to my RAM, grab what I'm trying to move, and tell me, here, this is what you need to move. Then the manager will be like, okay, then I take this, and I'm going to place it in here. So this becomes my B. All right? But not the address. Remember, this holds the address. So what it does is it grabs the value. It grabs the value of the value at the address of MAR. The address, I don't know, I didn't know how else to word it, but the address of mar. Okay, so whatever is at this address will go here, and at the address we have B, and so then we put B here. Okay, and so that's that's the register. Now if I want to add anything to it, I have something called an MBR. All right, so now we're gonna get rid of all this, and we're gonna do a second operation, which is called the MB, which incorporates the MBR. All right, so we're gonna move all this stuff, and we're gonna start again. You want to take a picture, and we're gonna get rid of all this stuff. We're gonna say, let's see, add. We're gonna say add B, add A, and B. Okay, and then I can say and store it in A. Okay, so now we're going to introduce our new component called an MBR. MBR. Now the MBR is the memory buffer register, and it's a data that the CPU needs to either read or write. Now why do we put in the MBR? It's because obviously my manager doesn't read directly from the CPU. So if I wants to read something, it reads it from the MBR. That's where it does the reading and the writing. It looks at it like, okay, what do I need to read? Here it is. All right. And so now, let's say we want to obviously add A and B. And so in order for us to add A, let's say we have some value in A already, which is 3. Okay. And so now this is B. B is right here. And so what I'll do is, well, first I have a register, right? I have 7 registers. So I have a register B. Okay. I'll change this to a different number. Let's change this to 10. And let's say I want to add something from this address. All right. So what will happen is the manager will go to my PC. My PC will already hold, this is going to be, let's say, step 01. My PC will hold 01, a pointer to 01. So the manager will be like, hey, PC, can you like pass the instructions to IR? And so PC will go to the IR and it will tell it, hey, you need to add. Okay. So the manager now goes to the IR, what do I need to do? The IR tell it, hey, you need to add. And then so it's like, okay, so I know, okay, now I need to add, but what am I adding? We'll go to the MAR and I'll tell it, hey bro, what do I need to add, you know? And so what the MAR will do is it will go to the counter, whatever this address is, we'll go to it and be like, hey, can I have your address? Remember, this also holds the address, the same address. So we'll go, grabs the address. So this is 01, which is the address. Address of number 10. Okay. So it grabs the address. Then the manager goes like, okay, now that I have the address, can you, since I need to add it, can you get me the value so I can fucking add that shit? And so what it does is it goes and it grabs the 10 and it sends the 10 to the MBR. Now the MBR holds the 10, right? MBR is where it actually holds the actual value of the register, whatever data is written there. Okay. And so now the manager goes like, okay, since now I need to add these things, I'm gonna transfer to the register B. So this is gonna be 10, right? And now I'm gonna execute, which is add A and B. And so what the manager will do is connect it to both. It will add A and B together, and then it will rewrite A and then write 13. When it does this, remember how I added it? What the manager will actually do now, will go back to the PC and increment it by 2. And so on the PC now what it becomes is 0.03. And that is step 0.3. Now you're going to think, why did it skip? Is because each instruction is 2 bytes long. Now, is this necessarily? No, it depends on the type of HAX you're using, your hypothetical system you're using. But in class, the prof used a hypothetical system of 2 bytes long. So each instruction is 2 bytes long. So every time, so you know how we first went to this memory, and this memory had this whole job in it, and we did the job? And so now that we did this job, what we'll do is increment by 2. And so what will happen is my PC will now point to the next instruction. And so it will go and update this. Let's say the next instruction is like subtract. Okay, and so like, okay, what do I need to subtract? Let's say you need to subtract now b from a. So now it goes to here, subtracts b from a, updates whatever, goes back, and it keeps going in a loop. Each time it finishes one instruction, that's a cycle. All right, which is managed by the clock. All right, and so that's basically right now inside your computer, your phone, your screen, everything. You have this going on, one cycle just ticking. Do this, do this, do this, do this, do this, do this. All right, and so that's really what HAX is. We are going to talk more about in detail about what all this stuff means and assembly, and we'll go from there.